Oh hey, you're probably wondering why I just appeared from behind a jug of antifreeze. And that's because today we're going to talk about how antifreeze works. Antifreeze lowers the freezing point of water, so the fluids in your car don't freeze up on a cold night. But antifreeze also raises the boiling point of water, so the fluids in your car don't boil over on a hot day. So we should start a trend, a movement. We should start calling it anti-boil freeze or anti-freeze boil. So next time you go to your auto parts store, say, give me a jug of anti-boil freeze. So let's go talk about freezing point depression and boiling point elevation right now. Why am I whispering? I don't know. Greetings everybody, greetings. Today we're going to talk about colligative properties of solutions. Let's first tackle that word colligative. What does that mean? Well, it's a fancy word that means collective. So when you add a solute to a solvent, you will find that the properties of the solvent, as it's now not a solvent, well, it's not just a solvent by itself, it's now part of a solution, properties will change. And so colligative properties are those things that change when you say dissolve something in water. So what are those things? There's about 3 of them. There is vapor pressure is going to be lowered. So, and I have to add the kicker. If the solute is not volatile, so if the solute has a very high boiling point and isn't something that evaporates really quickly. So for example, if you added alcohol to water, the vapor pressure would not go down because alcohol is volatile. As you may have seen before, we talked about boiling points. But if you added antifreeze to water, which by the way is ethylene glycol, or if you added salt to water or sugar to water, those things don't have a high vapor pressure, and so what will happen is the vapor pressure will then go down, and that will mean you had to heat it more. I'll show you a little cartoon later how that works. And the boiling point goes up. So we call this boiling point elevation. And so what also happens is the freezing point will go down. And we call that freezing point depression, which sounds like sounds like seasonal affective disorder, but it's really just that the freezing point will go down. So boiling point goes up, freezing point goes down, and you could just say, okay, I believe you, Mike, but I'm going to prove to you why that is. And then there's another one that we're not going to talk about today. We'll talk about it a little bit tomorrow, next time, excuse me, and that is osmosis. And you've always heard that, cliche joke like, oh, you're gonna sleep with your textbook under your pillow and study by osmosis? Yeah. Well, osmosis is extremely important, but when calculations are at issue like we're having today, we're going to actually do a lot of predicting boiling points and freezing points of things. Mostly a lot of key calculations involve boiling point elevation and freezing point depression. So now this is where I prove to you why that happens. So I'm going to make this little cartoon here, and you'll have to put up with my artwork. Yeah, I was dedicated. I drew all those circles. So let's say that this is water at whatever temperature. This is a thought experiment. And the vapor pressure of that water, it could be at room temperature, it could be warm, it could be at the boiling point. The vapor pressure is X. But now I go in there and add in some sodium chloride. And so let's make let's say these sodiums are now the red things. And I don't know if I have time to make let's just do the top few layers so you get the point. And so there's some sodiums, and of course you can't have sodiums without some chlorides. And as a stickler, I'm making the chlorine green because chlorine gas is green, but I'm being artistic, so let me go with myself. Now you know, because we've studied solids, that sodium chloride does not have and so on all the way down the solution. Sodium chloride does not have as very high vapor pressure at all. It's non-existent practically because it's ionic forces. And so before, you might have found that once in a while a water molecule could escape. Let's say it's at room temperature. At the surface, some lucky water molecule has acquired enough kinetic energy to vaporize and escape the liquid phase. But what happens now is if I go put salt in there, I'm going to block some, but not all, of that vaporization. And so it would be less. The vapor pressure would be less than X. I'm not going to be specific. We're going to talk about specifics in just a little bit. So I cut the vapor pressure down because I'm blocking molecules. That's all. It's as simple as that. I'm blocking molecules at the surface from vaporizing. Now, let's talk about something freezing. We've talked about water needs to arrange itself into little hexagons, and all the hydrogens need to line up with oxygens. And so when water freezes at 0 degrees C, those water molecules have to be in proximity of each other. Now you go and you throw some salt in there, you're interrupting the molecules, and they aren't able to line up like they should, and you have to cool it down more to drag more kinetic energy out of them, and so the freezing point is lowered. So if you really want to remember this, just let's take a little graph here. I'm going to make a little graph of, this is water with its landmarks, and what happens here is it's got its boiling point. Let's say we're at sea level, so the boiling point is 100 degrees C, and the freezing point is 0 degrees C. And now I'm going to go and I'm going to add some salt to it. So I'm going to go and bloop, dump some salt in there. And what's going to happen? Well, the freezing point, okay, I'll do the boiling point first. The boiling point's going to go up. And the freezing point is going to go down. And so we have this new kind of fangled thing here. We'll call this delta T B. Change in temperature of the boiling point. Sometimes they call it delta TB, delta TBP, excuse me. And we got this little change here. And that is called delta TF. Change in temperature of the freezing point. So we got to change there. So now the reason I do it that way is just think about it. You're stretching out that range. And do you notice that I made the freezing point go down more than the boiling point went up? That's usually how it happens. And you can say, Mike, why is that? And I'll be like, I don't know. It just is. And so we have equations to represent this, and I might as well write them down. So delta TB, this is called the boiling point elevation equation. Delta TB equals a constant. We're going to call it K. KB times molality of the solute. Remember I said molality is useful when we're heating and cooling things because it doesn't change. Its density, it doesn't change with density. It's a mass-to-mass ratio. So there is the boiling point elevation equation. And so what's up with that? That's basically something that says the change in the delta T of the boiling point, the change of the boiling point, I should say, is equal to a proportionality constant, which I'm going to go ahead and give it a name. It's called the boiling point elevation constant. All right. Constant. And by the way, kind of interesting little thing, this is for the solvent. So if you're going to dissolve something in water, you're going to go look up the KB of water. And you'd say, well, what about the salt? Well, actually, the water doesn't really care what's dissolved in it. It's going to just, it depends on how many particles there are. It doesn't even matter what the particles are. So if I had a molality of 1, the water wouldn't really necessarily, it wouldn't make much of a difference if that was a molality of sugar, or if it was, say, something like table sugar, or if it was like fructose, another sugar. It doesn't matter. What matters is the number determines how much the delta T goes up. And then the freezing point tends to go down because the constant for almost everything is higher. But you know what's really cool? This is, well, it's not that cool. I mean, this isn't that exciting, I understand. But the equation for freezing point depression looks very, very similar. Except the only thing it changes is what the symbol of delta T is and what the symbol of K is. So now, this delta T is going to be negative. I should write that in there, negative. This is going to be positive because boiling point goes up and freezing point goes down. Now, I'm going to go ahead and say sometimes you'll see a negative sign in the equation. Sometimes you will see a negative sign in the constant. That would be called the freezing point depression constant. And so you know what we should do? And to be honest with you, I've seen it both ways. I've seen the negative sign in the K, I've seen the negative sign in the equation, and to be honest with you, in the OpenStax text in chapter 11, I totally forgot which way it is. So let's go dig up a table of constants, and I'll flash that on your screen right now, and then we will go and solve a problem using both of those equations. And upon inspecting the table, my questions have been answered. You see that all those K constants in the table are positive numbers, and that means that the negative sign goes into the equation and not in the constants, according to that book. I've seen it both ways. So let's make a little negative sign right there for the delta TF equation. So, and you'll see it either way. But what you should do is really, if you did the wrong thing, you'd be able to rationale your way through it. Let's say you put 2 negatives in, that's a double negative, and you calculated a delta TF that was positive. You would know that's what we call in science perversion, because that does not happen. It's freezing point depression. So let's go ahead and read through this thing like a computer. Solution of ethylene glycol, well, I didn't give you a formula, but that's because I'm going to talk about it in just a little bit, is 50% by mass. Okay, so we might still be kind of clueless as to what this thing wants from us until I read the words boiling point and freezing point. Now that will trigger you to say, hey, that sounds like a freezing point depression and boiling point elevation equation. And the way I'm going to get that is through the equation delta T B equals KB M. M of what? The ethylene glycol. And that's, by the way, what's in the antifreeze boil. So, anti-boil freeze. Either way, I'm trying to start a movement. Delta TF equals KF times molality. So those are our two weapons. We're gonna whip out of our quiver here, swing, and then we're going to use those. And what I have also done is looked up the constant. So for water, the constant, the boiling point elevation constant is 0.52 degrees C per molality unit. So that means if you had a solution that was a molality of 1 mole per kilogram, the boiling point would go up 0.52 degrees, so it would become 100.52 degrees. And so, and I looked up this. This is, oops, the negative is, see what I almost did? I'm used to the negative being in the number and not the equation. So this would be 1.86 degrees C per M. And that came right out of that table I just showed you. So you're not, having to memorize nothing. The next thing is, of course, I didn't give you a formula for how many grams per mole is ethylene glycol, and that's because I wanted to sort of stop and pause and give you the formula. This is ethylene glycol. It's got 2 carbons, so it's got a chain to it, and then it's, hydrogen, 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 and then it's got OH. And then that would be ethanol, but it's like an ethanol with 2 OHs. So it's super polar because it's got 2 OHs. It's pretty darn heavy, and that's why its vapor pressure isn't very high at all. And so this is a liquid that you would mix, and when you go buy it at the store, they dye it colors so you can tell if you have a leak. And then, by the way, while we're at it, let's keep talking about ethylene glycol. If you drink that, now you say, why the hell would I drink antifreeze? Well, if you're a kid, it's sweet, it's green or orange or some fun color, and so it looks like Kool-Aid, but it will hurt you pretty bad. It's actually not ethylene glycol isn't poisonous. It's what your liver makes it into when it oxidizes it into oxalic acid. That'll kill you. So the funny antidote is they actually give you ethanol, and then your enzymes go chew on that and you excrete the ethylene glycol. So the antidote is to get drunk. They give you an intravenous dose. So that's just a safety trivia tip here. Okay, let's add up and see how many grams per mole this bad boy is. I got 2 carbons, so that's 12.01 a piece, so that's 24.02. This is back to Gen Chem 1. You got 2 hydrogens, or excuse me, 2 oxygens, that's plus 32. And then you got 6 hydrogens, that's plus 6.06, because hydrogens are 1.01 a piece. This is 62.08 grams per mole. What are we going to do next? We're going to use that number. And we're going to go back to what we did last time. Remember when we were converting percent to molality? And so my question to you is, how much solution do we have? It's a fantasy. You can make it any amount you want because percent is an intensive property. It doesn't matter how much 50% ethylene glycol I got, it's going to have the same molality no matter how much. So in my fantasy, I like to make things simple. It's a simple fantasy. I want to have 100 grams of solution. And the reason I want that is I want to make the numbers simple. So that means I got 50 grams of, C2H6O2. And I got 50 grams. And so I'm just 2 steps away from finding out how many moles per kilogram. You know what? I'm going to go ahead and pluck the low-hanging fruit. I got 0.05 kilograms. That's the denominator of molality. You know what's cool is to answer both parts of this problem, we're going to need to know the same molality number because it's 50%. So to calculate both the freezing point and boiling point, we really just need the same number. So that's kind of cool thing that this problem's being sort of nice to us. So now let's convert to moles. 62.08 grams. I made my 6 a little funny. That was supposed to be a 6. Now it's even funnier. 1 mole. So that's a little bit under a mole that we have. 50 divided by 62.08. And that is 0.805 moles. Little m is 0.0805 moles divided by 0.050 kilograms. And so let's find out what that is. That is 16.1 molality units. Boy, that's concentrated, right? Well, hey, when you make this up, it's, 50-50 is pretty darn concentrated. And so now what we're going to do next is we're going to crank that through each equation. And that's the next segment here. So we're going to use this as our M. We got our K's up above. And let's go ahead and crank it through. So delta TB equals the K number that we looked up in the book, 0.52 degrees C per molality unit, times 16.1 molality units. And guess what cancels right there? M. So let's go ahead and get that 0.52 times 16.1. 8 I'll make it to 3 digits. And those are facts. Those K values are not measured. Actually, no, 50% has 2 digits. I'm going to go ahead and, my calculator says 8.372. I'm going to go ahead and round that to 8.4. All right. And that's going to be my, and I know it might sound kind of like, it's somewhat, oh, well, first of all, what's that number right there? That is the boiling point elevation. So I want the boiling point. So boiling point is going to be 100 degrees C plus the delta T. So we have elevated the boiling point to 108.4 degrees C, and that's the first part of the problem. And you might say, that doesn't sound like much. Well, hey, that helps your engine from boiling over, and I know it's warmer than that, but it's also pressurized in there, so it's acting like a pressure cooker. And so now let's go ahead and do the same sort of thing. Delta TF equals minus, it's in the constant, 1.86 degrees C, and this is coming right out of the table, times 16.1 molality units. Now, the cool thing? When you're dealing with water with these kinds of problems, the delta T is the same as the T. So you're going to go and subtract this number, or add it, I guess, to 0, and it's going to be a negative number. 1.86 times 16.1. And that is 29.9 on my calculator. Of course, negative. I should have put the negative sign in there. And then because I'm going to do this to 2 digits, oh, hey, I didn't do this to 2 digits. Oh, okay. Call it 108. But okay, so this is going to be minus 29.946. Notice that the M's cancel, and this is degrees C. We're going to call it minus 30 degrees C. So this is funny. it's going to be 0 degrees C plus negative 30 degrees C is minus 30 degrees C. Now that gang is really cold. So if you think about it, 32 degrees, and then, you know, you got to take 32 degrees, so there's 9/5 in there. So Fahrenheit is 5/9 of a degree Celsius. So I got to take that 30, then multiply it by 9, divide it by 5. So that's 54 degrees below 32 degrees. That is negative 22 degrees C. So if that was 50% antifreeze, that is how cold you would have to get to make the fluids in your car freeze. Sometimes they don't use 50-50. Sometimes they use 70-30. And so if you live in Alaska, you might get down that far. But I've never seen it negative 22 here in the great Midwest. So there you go. That is, and then you see that there's a big difference because the K constant for water is much bigger for the freezing point depression constant than it is the boiling point elevation constant. But that's what would happen if you dissolve that much, and that's pretty concentrated. Ethylene glycol, we're stretching that range out, and we're making it go from 100 and 0 to 108 and negative 30. And so that's the thing. Now I'll give you a little heads up of what's coming next. Freezing point depression and boiling point elevation are a very important tool, because back in the days before instruments and fancy doodads like mass spectrometers, someone had to say, hey, we can burn sugar and find out it's 2 parts hydrogen to 1 part carbon and 1 part oxygen, but what's the formula of it? Well, you dissolve it in something, see what the freezing point is, go calculate the molality and then the moles and the grams per mole. So that's what we're going to do next. Next time we're going to do more problems with freezing point depression and boiling point elevation, and then we're going to talk a little bit of osmosis, and maybe I'll go on a tangent about my cucumbers. So thanks for joining. We will see you next time. Ciao.